Hey guys, my name is Sartek Camboj, and in this video we're going to talk about the insertion sorting algorithm. And if you're new here on this channel, we talk about computer science related topics such as data structures, algorithms, so on and so forth. So if you like that kind of content, make sure to like and subscribe. And without further ado, let's just hop right into it. So as you can see over here, we're going to talk about insertion sort, and insertion sort is basically a sorting algorithm where items are compared one at a time and placed in order sequentially. And if that doesn't make too much sense, basically what that means is that at each element, we look at each element and compare it and move it up the array in order to make sure that the array is being sorted in real time. That'll make a little more sense once when we go through the example, but that's kind of the gist of what the algorithm does. Its time complexity is O of n squared, and obviously you don't know what the algorithm does, but as we go through this example, just keep in mind and try to think about why the time complexity might be O of n squared, and at the end we'll talk about the reasons, the actual reasons why it is. So over here we have an example with the numbers 5, 4, 3, 2, and 1. And this is a good example because not only is this not sorted, but it's sorted in reverse order. So whenever like an array is sorted in reverse order, you know that you're gonna get, it's the worst possible case. So we can see exactly how the algorithm works in the worst possible case, and it kind of establishes the fundamentals of the algorithm. So essentially how it works is that we look at each element, and we move it up the array if it's smaller than its previous element. So for example, we start off with the number, or we can't start off with number 5, but there's no number, there's no value before the number 5, no element before the number 5. So we generally just start off on the second element of the array. And so in this case, that's the number 4. And so we compare it with the number before, which is 5. And because 4 is less than 5, we move this back. And so we get 4, 5, 3, 2, 1. Right, so at this point, one thing that we can know is that now we know that the first two elements of the array are 100% sorted, and we can rely on that in the future as we compare more and more elements further down the array. And so right now that we've looked at the number 4 and we've moved it as far as we possibly could, now we look at the number 3. And so the number 3 is less than the number 5, so we move that over. So we get 4, 3, 5, 2, and 1. But also note that 3 is less than 4. So we make one more comparison, right? We compare the 3 and the 4, and we notice that 3 is less than 4, so we move it up one more time. And so we get 3, 4, 5, 2, and 1. And so now we know at this point that the first 3 elements of the array are completely sorted, and when we move on to number 2, we can do the exact same thing. We compare 2 and 5, and we know that 2 is smaller than 5, so we get 3, 4, 2, 5, and 1. And then we compare 2 and 4. We realize that 2 is less than 4, so we can move it up. We get 3, 2, 4, 5, and 1. And as the last comparison that we do is between 2 and 3, and obviously 2 is less than 3, so we get 2, 3, 4, 5, and 1. And now we can see that we sorted the first 4 elements of the array just by taking elements and moving it up if they're smaller than their previous element. And as you guys can probably guess, the last element that we look at is number 1. And without doing too much like comparisons or talking about it too much, we know that 1 is less than 5, it's less than 4, it's less than 3, and it's less than 2. So we know that 1 will be moved all the way to the front of the array, so we get 1, 2, 3, 4, and 5. And now over here we have a completely sorted array. And one more example that we can kind of look at is just a shorter one. We can look at 2, 3, 1, right? So that was example 1. That was a worst case scenario, and in a little bit we'll talk about the time complexity and why it's O of n squared. But if we look at this example right here, 2, 3, 1, we start off over here. We can see that 3 is not less than 2, and so since it's not less than 2, we don't need to move it at all, and so we can just move on to the next element. And because of this, we also know that 2 and 3, the first 2 elements of the array are completely sorted, and when we look at 1, we can compare it to 3. Obviously it's less than 3, so we get 2, 1, 3, and we compare 1 and 2. Obviously it's less than 2, so we move it forward and we get 1, 2, and 3. And so here's a sorted array. So the important thing to know here is that as we move forward in the array, we know that whatever elements that we've traversed, those elements are in sorted order, or those number of elements are in sorted order. And so the last thing we have to do is we have to talk about the time complexity and why it's O of n squared. And so essentially the reason why it's O of n squared is because you're going over every single element, right? We went to 4, 3, 2, and 1. And if you notice in this scenario, we moved it back to the front of the array almost, not in this situation, we moved it to the front of the array every time. And remember when we talk about time complexity or space complexity, we always talk about worst case scenarios. And so essentially what we have here is that we're moving it back to the front of the array and we're moving it n times every time. And so essentially what's happening is that for n times, we move it back n spots, right? So essentially what we get is we get an n squared time complexity as every single element is being moved to the front of the array. Hopefully that made sense, and if that didn't make as much sense, or if it helped, make sure to comment, and if you have any questions, just leave a question below and I'll try to help you out. Other than that, thank you for watching and have a nice day. Bye.